Hi everyone, in this video we're going to look at context-free grammars again, and particularly we're going to look at how to simplify them. The only thing you need to remember are the basics of what a context-free grammar is, again particularly with respect to the rule rewrite system. So before we start actually looking at the algorithms, we're going to look at a motivating example and use our brains to try and figure out how we could simplify this, and then that'll give us a little bit of a kernel of an understanding of how to, or actually what the algorithms that I'm going to talk about afterwards are actually doing. So if we look at this grammar, we have our set of terminals, so symbols that can actually exist in the final string that the grammar generates, and a set of non-terminals, and we have our start non-terminal here, and then this is our rule set. I want you to look at this for a second, so just pause and look at this for a second and see if you can identify any things in here that are problematic, that could be removed without changing the final language that this grammar accepts. Sorry, not accepts, generates. So, I hope you've done that. But if we look at the rule here, we have a problem. Anytime that we end up with a C, the only thing that we can expand it into is something that contains a C. So let's say I'd followed this expansion here. So S went to AC. Now C can expand into BCA, but we've still got a C there, so we've got to expand into BCA. And we continue on forever. At no point do I end up with something that only contains terminals. So this subtree here never generates a usable string. Remember that for a grammar to generate a string, it has to eventually result in something that's only from our alphabet sigma. So obviously this non-terminal here isn't producing any useful strings. So I can remove that, and then obviously I need to remove anything that uses that as well. Now if we look at this rule here, D goes to AB, we notice that if we look through the rest of the grammar, there's no way to actually ever produce a D. So we can call this this non-terminal, an unreachable non-terminal. We can never get there. So if I were to just wipe that out from the grammar entirely, and then wipe these from the set of non-terminals, then I have a grammar that still produces just as many strings as it could before. So unfortunately we don't just have a nice little min DFSM algorithm that simplifies everything down to the simplest version. We can, however, use a few algorithms that do part of the job. So the first one is to remove those unproductive non-terminals. So in our previous one, C was unproductive because it never gave us a useful string. So the algorithm goes as so. First important step is that we mark every non-terminal to start with as unproductive. And we mark every terminal, so the letters that end up in the final strings, as productive. And then what we do is we go through the rules and check them, and then if they satisfy a certain constraint, then we will say that the non-terminal is now productive. So basically, if we look at a rule and we see that the right-hand side of it contains only things that are productive, then obviously that non-terminal is productive. So for the first case, the only things that are going to be productive are our terminal symbols. So if I have terminal symbols A and B, and I have some rule T goes to AB, well obviously T can produce a useful substring, so immediately T becomes productive. So what we do is we keep iterating through this recursive over and over again, and eventually we will get to a point where we look through each of the rules, and we can't, and this rule has not been satisfied, so at that point we stop. Then we get all of the rules, every non-terminal symbol that's still left unmarked as productive, and remove it from the grammar. And obviously we then have to remove all of the rules that contain an unproductive symbol. And then we remove our final grammar. So let's follow the algorithm step by step through our motivating example grammar. So in this case, we're from what we looked at before, we're expecting to end up with C being an unproductive non-terminal. So what we'll start with, we'll have a set U of unproductive non-terminals and a set P of productive symbols. And then I'm going to work in a different color here. So the first thing we do is all of the non-terminal symbols are unproductive. So S, A, B, C, D. And all of our terminal symbols are productive. So little a and b. And then I would also put in EPS here because, yeah, you can either put it in there or you can remember that when you're looking at this thing here, that when you have a rule where the right hand side is just EPS, then every symbol is obviously productive. So let's look through here. If we look at the rule A goes to epsilon, we can straight away see that everything on the right hand side of that rule is marked productive, i.e. nothing on the right hand side is unproductive. So we can straight away move A over to our list of productives. Now we go back through and start right from the start again and look through, and we now see that B here has only elements from our productive set P in it. So we can move B over as a productive non-terminal. And so on, we can look through and we see now that the rule D goes to AB means that D needs to be over in this set of unproductive non-terminals. So even though we know from our motivating example before that D is not going to be a useful rule, it is still a productive non-terminal for this algorithm. So we'll need more than one method to end up simplifying the grammar in the way that we did before. Finally, if we look now that we see the two rules for S only contain, there is a rule for S which only contains productive terminals, so we can move S over to our list of productives. And now, if we go through all of the rules, we don't have any rules where there is a terminal currently in the unproductive set, which the right-hand side only contains productive symbols, because the only symbol rule that we have to look at that has an unproductive terminal on the left is this one here. But unfortunately, it contains the exact symbol that we're looking at as an unproductive symbol. So when we go through this last iteration, we get to the end and we haven't made any modifications, so we drop out. And now we remove from G all the unproductive symbols. So in this case, the only symbol remaining in the unproductive set is C, so we remove C. Then we remove every rule that contains an unproductive symbol, whether it be on the right or the left-hand side. Now this rule contains an unproductive symbol, and this rule obviously contains an unproductive symbol. So our grammar at the end just consists of S goes to AB, A goes to all of the things it went to before, B goes to AA, and D goes to AB. Now, if we want to keep simplifying it, we can use this algorithm, which figures out the non-terminals that are unreachable. So in our motivating example before, we remember that we found that D wasn't very useful because we could never get to a point where we actually had a D in the working string that our grammar was generating, so we could never use it to expand. So the algorithm for that is start with the start non-terminal, and then we're going to look at the things that we can find from it. So we mark the start non-terminal as reachable. We mark all the other non-terminals as unreachable for the moment. So, like before, we'll have these two sets, one of the things that might potentially still need to be removed, and then another set that we're gradually building up of the things that we clearly need to keep in the grammar. So we keep going until we keep going through a pass through all of the rules, just like before, until we get to the point where we haven't made any modifications, then we drop out. And at each point, we look for a rule where we have X goes to something where there is a non-terminal in there here. So that's what this says. The set difference between V and sigma is exactly the set of non-terminals. So we're just looking for rules that somewhere in them contain a non-terminal. Where the rule that we're looking for is one where the left-hand side has been marked as reachable, but that non-terminal in the right-hand side has not. then we can mark that non-terminal as reachable. So basically every time we have a rule, let's say we have S goes to AB, if S is reachable, then we'll mark A as reachable, and then we'll look at that same rule again and we'll go, okay, yep, B is obviously reachable as well. So basically we're just looking through the rules and seeing if we can eventually expand out to get any particular non-terminals. Once we've gone through all of the rules once without changing any of them, then we drop out of that loop and we simply remove all of the symbols that are still left in the unreachable set, and we remove all of the rules that have that symbol on their left-hand side. Because obviously we won't need to worry about removing the ones that have it on its right-hand side, because if any of them existed, then during this iteration here, we would have marked that rule as reachable. So let's go through our motivating example here, and we're expecting at the end to see that the non-terminal D is going to be marked as unreachable. So we'll have our sets just like before. We'll have unreachable on the left and reachable on the right. Doesn't really matter exactly how you do this. And we mark S as reachable. Obviously, because we're starting with it, it doesn't make any sense for that not to be unreachable, or not to be reachable, sorry. But all of the other non-terminals are initially marked as unreachable. Now we go through each of the rules in this number 3 loop that we've got here. And any time where we've got a reachable symbol on the left-hand side, so in this case S, and some unreachable symbol on the right-hand side, we move that unreachable symbol over. So if we look at the rules that contain S on the left-hand side, we've got these here. So immediately we can move A over to the reachables, we can obviously move B over to the reachables, and C, because we can expand out to generate some A, B or C immediately from an S. So that was pretty quick. Now we go back through and look at every rule. Now we have to look at all the rules that contain S, A, B or C on the left hand side, and then see if any of them contain something that is currently in U at the moment on their right hand side. And we look and we see that there is no D's on the right hand side, so we don't change anything. So at this point we've done an entire pass and we drop out. So the symbol that is left as unreachable is D, and so now we remove D from the set V, and we remove every rule that has that on its left hand side from R. So we remove this and we're left with that grammar. So you can see that if you followed either of these 2 algorithms one after the other, you would end up with what we got before from our informal simplification of the grammar that we did at the start. So what I hope you got from this was an understanding of how we can do some things to remove useless non-terminals from a context-free grammar so that we can simplify them. And I hope you also might have gotten a little bit of an understanding of why it might be a lot more difficult to simplify a context-free grammar than it will have been to simplify regexes or regular grammars, not that there was much simplification to do there anyway, or finite state machines.